In this video, we're going to give a brief introduction to the constitutive laws governing hyperelastic materials. I will focus on the main concepts for the constitutive model, and I will leave out some of the derivations for the students who are interested. The detailed derivations can be found in your online notes. Recall the equations we presented for linear elastic materials in which the strain energy per unit volume is given as an explicit function of the stresses or strains at a point. This ensures that for linear elastic materials, energy is preserved, which means the amount of energy stored is function of the stresses and the strains independent of the loading path. I'm going to digress for a moment to talk about path dependence and path independence. In general, if I have a well-defined smooth function, let's say from r squared to r, let's call it denoted by u, then the infinitesimal change in u, du, is equal to partial u by partial x multiplied by the infinitesimal dx plus partial u by partial y multiplied by dy. The integration over du from point 1, characterized by the values x1, y1, and u1, to point 2, characterized by x2, u2, and y2, is basically equal to u2 minus u1. This is equal to the integration of two terms, partial u by partial x integrated over x and partial u by partial y integrated over y. Since u2 minus u1 is constant, this integration is independent of the path between x1, y1 and x2, y2. And from the properties of differentiation, the second derivative of u with respect to x and y is equal to the second derivative of u with respect to y and x. If we have the differential form, du is equal to a function a of x and y multiplied by dx plus a function b, x and y multiplied by dy, then we have two possible scenarios. The first scenario is that the expression is called exact differential, and the integration over du is path independent. That's true if and only if partial a by partial y is equal to partial b by partial x. That in that case, there is an explicit form for u that is function of x and y. The second case, if we have an inexact differential, the integration is not necessarily path independent, and that happens when partial a by partial y is not equal to partial b by partial x. There is an example in the online notes where the energy is not preserved if the relationship between the stress and the strain is not symmetric, where we do not have an exact differential. So what does this mean exactly? So here we show a schematic representing what we presented in the previous slides. The blue surface represents u as a smooth function of the variables x and y. X and y, and we get the blue function. The value of u2 minus u1 is constant and is equal to the integral along any path between 1 and 2. We've got a green path here and a red path here. The total change, which is obtained by integrating the derivative, is independent of how we get from the state representing point 1 and the state representing point 2. Here is the Mathematica code that I used to generate the previous diagram in case you need to replicate it. So what does this mean in terms of mechanics? Let's see this example. We have an elastic material that does not dissipate any energy during deformation. Let's assume two states of deformation. State 1 with mechanical strain energy density or energy content U1, and state 2 with mechanical strain energy density U2. We can move from state 1 to state 2 using a particular path. Path 1, in which we choose to apply deformation on one side first and then apply deformation in the other side. Or we can move go from state 1 to state 2 using a different path. Path independence guarantees that the energy U2 minus the energy U1 is the same whether we go through path 1 or path 2. So the energy is independent of the path of deformation. So if I have the differential du is equal to a dx plus b dy, for u to be independent of the path, a has to be equal to partial u by partial x, and b has to be equal to partial u by partial y. When I apply this to mechanics, if the increment in the internal energy is equal to each component of the stress multiplied by the component of the strain, for example, sigma on 1 delta epsilon on 1 plus sigma to 2 delta epsilon to 2 plus and so on, then for the energy to be neither created nor dissipated, or to be independent of the path, the energy has to be well-defined functions of the strains, and each component of the stresses has to be equal to the derivative of the energy function with respect to the corresponding strain component. In section 9.21, we showed that the increment in the strain energy per unit volume in the deformed configuration is equal to the sum over all the components of sigma ij multiplied by the corresponding change in the strain component delta epsilon ij. We also showed that the increment in the strain energy per unit volume in the reference configuration is equal to the sum over all components of the first PO like Kirchhoff's stress tensor multiplied by the corresponding increment in the deformation gradient Fij. On a side note, remember that the increment df of the deformation gradient is also equal to the increment in the displacement gradient, which might come in handy in some applications. So, to describe the material as elastic and the energy to be independent of the path, the components of the first Piola-Kirchhoff stress tensor are equal to the derivative of the function W with respect to the components of the deformation gradient. dW is equal to Pij multiplied by dFij, and Pij's are equal to partial W by partial Fij. So hyperelastic materials are materials whose constitutive law is described by a strain energy potential function W, and W can be given as a function of the deformation gradient F. In the next few slides, we will investigate the possible forms for such energy function to ensure isotropy and independence of the coordinate system chosen. First, let's consider the independence on the chosen coordinate system. We will term this independence frame invariance. Given a deformation described by the deformation gradient F, so this is the original or the reference configuration, and this is the deformed configuration, they are related by the deformation gradient F, the strain energy per unit reference configuration is equal to W as a function of F. If we choose a different coordinate system, then the energy could be a function of QF. So basically, if we rotate the object in space after this deformation, then the final energy would be equal to W of Q of F. You can think of this as deforming the object by F and then rotating it by Q. The final energy should be the same under this rigid body motion or under a simple change of coordinate system. This leads to the following mathematical statement. For any choice of rotation, the energy of QF has to be equal to the energy of F. This implies mathematically that the energy has to be a function of the U, which is the positive square root of F transpose F. And if you, I encourage you to visit the section on the deformation gradient where we introduced this deformation measure. This is actually something good to have because because it actually ensures that our Cauchy stress is symmetric, and this is rigorously described in your online notes. We will now consider that the material is isotropic. Of course, you can extend this. You don't need to use isotropy, but we're just going to present the case of if the hyperelastic material is isotropic. So if it's isotropic, what does that mean? It means given a reference configuration, and I can apply a deformation gradient F and get a deformation, and the energy is now equal to the energy is function of F. If I choose to do a rotation and then apply the same F, then the energy is equal to W of FQ. The reason F and Q are in this order because I apply Q first on the vectors and then I apply F. And so the W is equal to a function of FQ. You can think of this as rotating the object by Q and then deforming the object by F. If the material is isotropic, then the final energy should be the same whether it's W of F or W of FQ. This leads to the following mathematical statement. For every Q, where Q is a rotation matrix, W of F is equal to W of FQ. Now recall that F can be written as P multiplied by a diagonal matrix multiplied by Q transpose, where D, the diagonal matrix, has diagonal components lambda 1, lambda 2, lambda 3, which are the principal stretches, or the positive square roots of the eigenvalues of F transpose F. And so this tells me that if I have an isotropic frame invariant hyperelastic material, I can simply write the strain energy as function of these three numbers. It turns out that you can write for any isotropic hyperelastic material, you can write W as function of the following sets of components. The principal stretches lambda 1, lambda 2, lambda 3, the squares of these lambda 1 square, lambda 2 square, lambda 3 square, the first invariant of U, the second invariant of U, the third invariant of U, or the three invariants of U squared, or the first invariant of U squared, the second invariant of U squared, and J, which is the determinant of F. All these are equivalent. You can, and the proof of this is online. You can also write it as a function of, or you can choose to write the energy as two functions. One function that is with no volume change, and another one associated with volume change. The one that's associated with volume change is a function of the determinant of Fj, while the other term is function of I1 bar and I2 bar. I1 bar and I2 bar are the first and second invariant of F bar transpose F bar, and F bar is equal to F after dividing by the determinant of F, the cubic root of the determinant of F, and that guarantees the determinant of F bar is equal to 1. So basically normalizing F according to the volume change. Whatever form is chosen, it should in most cases abide by the following. The minimum energy should be attained when the deformation gradient is equal to the identity matrix or to a rotation. The energy should also increase to infinity when the determinant of F is going close to 0 or the determinant of F is going to infinity. If I bring a material and I squish it, the energy has to increase, the deformation energy, and if I expand it infinitely, the energy has to increase as well. Similarly, the energy should increase to infinity when the stretches increase to infinity. The first form that we are going to present is the form where the energy is written in terms of the first two invariants of C, namely I1 and I2, the first invariant of U squared is F transpose F, and the second invariant of U squared, which is the second invariant of F transpose F. J is the determinant of F. The first Euler-Kirchhoff stress tensor is the partial W by partial F. Now I've written W as a function of I1, I2, and J, and so to find partial W by partial F, I need to take the derivative of W with respect to its components, or I1, I2, and J, or its variables I1, I2, and J, and then multiply by the derivative of these components with respect to F. So there's a lot of work that we need to do a priori to find these derivatives. and I have done that work online. You can find the expressions. I've already written them for you here. Partial I1 by partial f is 2f, partial I2 by partial f is this expression, and partial j by partial f is this expression. And so this would make it very easy to find the expressions for f. All we need to do is find the expressions for the derivatives of w with these variables, and then we can find the first Piola-Kirchhoff stress and the Cauchy stress tensor as well, because we know the relationship between the Cauchy and the Piola, and so it's a simple arithmetic. Just find these expressions and we'll be able to find, simple algebra. Using this expression we can find the Cauchy stress tensor. In section 3.2 in your online notes provides the details of calculating the derivatives of the I1 of u squared with respect to f, and the details of the other derivatives as well. I'm not going to go through the details here. I will leave it to the students who are interested. Alright, so knowing these derivatives, I can then substitute. Instead of partial I1 by partial f, I'm going to put 2f. Instead of partial I2 by partial f, I'm going to put 2I1f minus 2f f transpose f. And instead of partial j by partial f, I'm going to put j f and negative transpose. And knowing the relationship between sigma and p, and substituting, I will get the expression for sigma. These expressions are analogous to writing an expression of the stresses as functions of the strains in the linear elastic case. Here is an example: the incompressible Neo-Hookean material model that has this expression with one material constant mu. Because it's incompressible, J, which is the determinant of F, is set always to equal 1 by applying a pressure P. This is usually implemented in any formulation using this material. In order to incorporate P in the solution for the stresses, W is sometimes written in this form, adding a term which is equal to the hydrostatic pressure, that it ensures that volume is equal to 1 multiplied by J minus 1. You can see that this adds nothing to the energy because J is always equal to 1. On the right hand side here are the general expressions for P and sigma as we obtained from the previous slides. All what we need to do is find partial W by partial I1. Partial W by partial I1 is equal to 2 mu. So 2 mu, here's 2 mu, multiplied by 2f gives me 4 mu f. And then partial W by partial I2 is 0. Partial W by partial J is equal to P, multiplied by J f negative transpose gives me this expression. The relationship between P and sigma is known, so I can calculate sigma right away. And you can see here, the stress is equal to an expression function for mu and another expression function of this hydrostatic pressure P. Here's another example, the compressible Neo-Hookean material model. The difference between this material model and the previous one is that we added expressions function of J, which is the determinant of F. Again, this is the general expression for P. First, I need to take the derivative of W with respect to I1. The derivative of W with respect to I1 is 2 mu 1. Multiplied by 2f gives me 4 mu f. The partial W by partial I2 is 0. Partial W by partial J, I will have to differentiate W with respect to J here, and will result to this expression. Will result in this expression. Again, using the relationship between P and sigma, I will be able to find this expression for sigma. Similarly, you have here the incompressible Mounier-Rivlin material model, and I will leave the details for this for the students who are interested. In this slide, I'm going to go through or present the main forms that exist in the commercial software abacus. These are given in terms of I1 bar, I2 bar as indicated before. So the energy is given as a function of I1 bar, I2 bar, and of another component that's function of J, where J is the determinant of F. Again, To find the first Piola-Kirchhoff stress, we take the derivative of W with respect to the variables, and then multiply by the derivatives with respect to F using the chain rule. In your notes, I go through the details of finding the derivatives of I1 bar with respect to F and I2 bar with respect to F, giving these expressions. As an example, here's the compressible Monnier-Rivlin material model. Here's the expression for the energy. To find P, all I have to do first is calculate the derivative of W with respect to I1 bar. So W is a simple number, it's a constant multiplied by I1 bar, so the derivative is simply this value. Multiplied by partial I1 bar by partial F, here's partial I1 by partial F, it's a simple substitution here. And so on. Using this expression, I can quickly find the expression for P, and knowing the relationship between sigma and P, I can find the expression for sigma. In the following few slides, I will provide a method to provide an estimation for the material parameters of hyperelastic models given their initial linear behavior. Given initial elastic moduli, the shear modulus and the bulk modulus in particular, we will see how we can relate those to these constants that appear in these forms. First, we will apply a general shear deformation. This general shear deformation is applicable to the compressible material models W1 and W2 and the incompressible material models W3 and W4. The corresponding shear strain, if this was linear elastic, is equal to G alpha. You can see here this is the shear strain alpha. And if this was a linear elastic material, sigma on 2 will be equal to G alpha. If I substitute in the previous forms in provided, that gives me the stress tensor given this F, you'll find that sigma, the stress tensor associated with the first energy is given by this form, the second energy is given by this form, and so on. I'm going to pick sigma on 2 in all these forms. In all these forms, I'm going to pick sigma on 2, and then I'm going to set sigma on 2 equal to the value of the shear stress in the linear elastic case, and then I can find this direct relationship between these constants C10, C10, C01, mu1, and mu2, and the shear modulus G. In fact, in your if you are a user of hyperelastic materials and you read the Abacus manuals, they actually give you those relationships in the manual so that you can find the good estimation for these constants for your hyperelastic material. For the compressible material functions, energy functions, we need to find a relationship between this material constant D and the bulk modulus K. In order to do this, we're going to assume a deformation gradient that's equal to alpha multiplied by the identity matrix. In the linear elastic case, if you actually do the calculations, the stress is equal to a hydrostatic pressure, P, multiplied by the identity matrix. And this hydrostatic pressure is equal to K, the bulk modulus, multiplied by the volumetric strain. The volumetric strain is equal to delta V over V, or in large deformations is equal to the determinant of F minus 1. The determinant of F is equal to alpha cubed. If I now use the expressions for sigma as a function of F, F here is given, I've got the two forms, I can find the stress given this F. Here's the stress for the first expression and the stress for the second expression. Because this, these two forms separate J from the I1 bar, and I2 bar, you'll find that the stresses for these two energies are identical. This corresponds to the hydrostatic pressure in the linear elastic case. It is actually a hydrostatic pressure, so 2 over d alpha cubed minus 1. When I equate 2 over d alpha cubed minus 1 to k alpha cubed minus 1, you see right away that this d constant that appears in these expressions is related to the bulk modulus by the relationship 2 over d is equal to k. So this served as a very, very brief introduction to hyperelastic materials. There's more information, more mathematical statements, proofs, and examples on the website for those students who need to learn more about hyperelastic materials.